I guess in this matter we don't define multiplication by zero.
Nope, there's no one in there.
Yeah.
There's no one in. There's no element in there, so it's going to be empty set.
The Cartesian product is the empty.
Yeah,
Oh yeah.
you're right.
Cartesian product is
It's the empty set. Actually,
It's all the ordered pair, but there is no ordered pair. There's only these
yeah.
sets of one
it's
element.
the set.
If we define these ordered pairs.
Yeah, we're continuing it with something that has no element. So we have 5 comma, right? That's substitution. Okay. So how do we define an ordered pair set theoretically? We talk about ordered pairs as just being something comma something. But we want to describe everything in terms of sets. So now how can we turn this into a set? Because we want to make sure that 5 comma 3 is different than 3 comma 5. We want to have this happen. Well, thanks to Kuratowski, thanks to Kuratowski, we have the Kuratowski definition of the ordered pair. We denote the ordered pair with this symbol, and we will construct it as follows. It is the set containing x and the set containing x and y. So let's check that this is in fact different than y comma x. This is y and x comma y. So by extensionality, these guys aren't the same. The set containing x is in here, and the set containing y is in here. So these are not equal as sets. So now we have a distinct way of talking about the coordinate pairs as being elements of these guys. So now let's go back and look at this one. So so the ordered pairs are going to be, I haven't prepared this.
Why do you want to get zero in this Well, I have a very theoretical mind. The party also consider zero a number. I never, well, I know why. But why do you want to get it wrong? After all, piano didn't consider a number of the time. It's hard to keep one. If they want 10 successive, 10 successive, 10 successive, if you don't have any powers,
You still have to
it's also personality. Eventually, you need the product to see. It's a good according to properties that you have. This is the research, it's a good research.
Yes, with the human functions set x
Did
comma y
instead of all
such that x belongs to A and y belongs to B. A in the Cartesian product contains B.
And the elements of that look like.
This is why I have big Y in the middle.
Yeah, big Y has no element.
So you're doing
the
the set containing x and the set containing x.
If there are no elements in y, then it's impossible to have all that pairs, or you don't have all that pairs. So it's together.
So it's empty.
Well, I don't know how much more set there is. Well, does anybody have any questions or comments?
You define addition on what domain? It's a function.
Well, we define addition to be an ordinal that is in bijection with a set constructed from the two ordinals. We take the two ordinals, we construct the set, and we consider the cardinality of that set.
Do we consider omega an ordinal?
Well, yes, omega is indeed an ordinal.
But then there is no unique ordinal that is in bijection, which is sum of omega and something else.
The definition, there is a much more rigorous definition of what an ordinal is. But I chose to define an ordinal this way for the means of the talk. But if anybody's interested to see a much more rigorous definition of an ordinal, they can talk to me about it later. But I was trying to keep this within the frame of time I have here. What? Well, this is how we get what we want. We have something in mind. Yeah.
Actually, everybody respects only does not rigorously introduce. People try to rigorously introduce everything from the basis of sets. If we start with sets, we have to learn to define everything from the basis of sets. For example, everything has to be done by using sets. You can give many things are put under the carpet. For example, Eric really used the expression, let's consider the Cartesian product set. How do you know this is a set?
Oh, okay. Well, in order to do this, I actually need another axiom that I haven't used called the replacement axiom. But there's an axiom to allow us to create the set X Cartesian one.
On the other hand, I don't believe there is a person on this earth who can explain this to one another.
Yeah. I learned this material through the course of a semester, not 1 hour.
More expensive.
And eventually, there is a belief.
That was the point of the lecture, is that we still have to believe that the natural numbers exist. It's an axiom. That was
But you really should why we need it to be there.
yeah, because we can't construct it given the other axiom. You have to assume it exists in order to start playing it.
You know, there's a different set of axioms. What happens to an axiom?
I know that there are other systems of axioms. The axioms that I'm using are part of Zermelo-Fraenkel.
Here you go, sir.
These are the axiom of Zermelo-Fraenkel. There are other sets of axioms that you can use to do everything else. But this is just, mathematicians have standardly used this list as just, this is the list that mathematicians generally accept and they use.
I suppose many systems, for example, Hilbert has a system, Carl has a system, and also stuff. The most useful and intuitively close to our human beings is how to put them out. Some people go to believe that when you put that but it works. The belief that I mentioned here is regarding the following. People, they want to find everything by using certain part of network. Example set theory. It turns out that if you start going deeper in the set theory, there is a moment in which you have to rely on logic. Then you have to prove that the logic is well defined. When you start defining well logic, you go back to the numbers in a certain way. It turns out that all these very basic things in mathematics, they are related to their equivalent. There is no way to show their system. We believe this, because it is not what we do. And so far, everything is possible. There are mathematicians who do not accept many parts of the system. Yeah. There is an example part of the system is the axiom of choice. There are mathematicians who say this is illegal. This axiom of choice is so powerful that it can prove many impossible things. For example, we want to have this discussion with the macro last year, but before as well. By using the axiom of choice, you can show that in three-dimensional space, you can start with the sphere of dimension 1, the whole of dimension 1. You can split it into parts, assemble it, and assemble two equal spheres which will be this. By using the axiom of choice. Start with one sphere and all of a sudden double. What can you do? In the plane, for example, it's impossible to start with a physical and doubt. But in the three-dimensional space, it is possible. And some mathematicians will say, no, I don't trust this. I don't. On the other hand, if you don't have that kind of trust, you don't get many things in the field, including the functional analysis, including many, many, many things. And Hilbert said, nobody can get us out of the element that country. Let us see.
Yeah.
Let's do such, because without it, it's too.
The nice world that we
No,
live in isn't so nice.
But one of the greatest of them is not accept. They say, no, we are better than that. We can do it. Not without it. For example, the computers, we don't accept it. But the computers work only with natural numbers. Natural numbers don't do this. If you want to go beyond, then you have no power. Again, the story of set theory, and in particular the counting of natural numbers, is long, very interesting, and useful in some areas of mathematics. But what the modern mathematicians do, they believe this is true. And after all, Newton's hypothesis is much more advanced.
Oh, yes. Are there any more questions? Thank you guys for coming.